Good evening, everyone. Thanks for being here for the last talk of the day. My name is Manasi Navare. I work for Intel. I work on the i9-15 graphics kernel driver. And today I'm going to talk about this fun project I've been working on for last few months. So who all here has played with the 8K displays? Anyone? Okay, that's cool. I see few hands. So maybe you can help me figure out things that are still open. Um, So I was playing with the 8K displays, and along with that, there was another challenge for me to get it working with the two CRTCs and get rid of the screen tearing. So that really put tears in my eyes, right? So let's see how it got fixed. So just a little bit of background on 8K and how 8K maps in terms of the display bandwidth. So this is the 8K frame, 7680 by 4320, and that's 33 million pixels per frame. And when you start streaming it at 60 hertz, that's like 1980 million pixels per second. What that means in terms of the display bandwidth is it requires 48 gigabits per second. So how does that map or compare to what we have available on the current DisplayPort specification and the bandwidth? Um, the first spec that came out supported only 10.8 gigabits per second with the lowest rate RBR, HBR for DP 1.1. Then with HBR2, we could do 21.6 gigabits per second, so it was fine for like 4K at 60. And then the latest spec that we have so far is HBR3 with DP 1.4, and that can do up to 32.4 gigabits per second. So is that really enough to do 8K streaming over single DP connector yet? Clearly no, because the required bandwidth, as I said, is 48 gigabits per second. That's for 60 frames per second. But for applications like VR, you could require more, so upwards of 48 gigabits per second. And what we have is only 32.4 gigabits per second. So no go there. So what we have currently in the market is, this Dell 8K monitor that can do 8K using the two DisplayPort connectors. And this is how the setup looks like. And then the other thing that actually limits the display resolution that you can output on any hardware is how fast that a pipe can run. So on Intel hardware, the maximum pipe pixel rate that we can do is 2 times the CD clock. So like for example, on the latest platform, the Ice Lake Gen 11, the CD clock, maximum CD clock is 652 megahertz. And the maximum peak pixel rate that we get is only 1290 megahertz. And clearly not enough for 8K at 60, which needs about 2000 megahertz. So for any 8K or higher resolution, we have to split it across two CRTCs or two pipes on the Intel current gen platforms. Oh no, sorry. Go back. I don't know, I just have to go back. Okay, we're back. So what do we have currently with the 8K setup with the dual pipe and dual port configuration? The 8K monitor, Dell 8K monitor advertises itself as a tile display. So it sends out the tile information through the monitor's EDID or the display ID block in the EDID. We parse that and split that into two tiles and send it on each of the CRTCs. So we send half of the 3840 by 4320 on one CRTC and the right half on the second CRTC. So clearly that needs only 24 gigabits per second, and you can send it on each on a single DisplayPort. And then the final picture gets stitched and you get the final DisplayPort 8K output. But what are the challenges here with the two ports? So you have the 8K frame, and then it gets split into two tiles, and then it gets connected across two DisplayPort cables to give the final output. But then the mode sets actually happen sequentially. So you do a mode set on pipe 1, and then you do a mode set on pipe 2. Now we talked a lot about the V-blank signal and the timings, and the only time when we start seeing the next frame is on a V-blank. That's when the page flip will occur. And because the two ports are used here, which may or might not be synchronized, most of the cases, if you don't have anything synchronizing the two ports, their V blanks are going to be offset. So you get a V blank on the first DP port, and that's when you do the flip on the first port, you start seeing the DP output on the left half of the screen. And then you get the V blank 2, that's when you'll see the page flip on the second half of the screen. Now, if it doesn't happen in the same vertical blank, then what you see is something like this, where it's just off, and it's all the line counters, frame counters, everything is off, and you see this kind of tearing on the display. And this is not specific to 8K. We already have these kind of bugs with 5K tile displays, sometimes with the 4K tile displays. Anytime where you have to have a tile display output across two CRTCs, you see these kind of tearing artifacts. So how do we fix it? So we have this hardware solution called Transcoder Port Sync, and this mode basically forces the two ports or the two transcoders that are involved in the tiled mode to be in synchronization. So it just operates in this master-slave mode, and then from there on, the timing on both the master and the slave or multiple slaves is in the lockstep mode. So in terms of the timing, this is how it looked like before we had any transcoder port sync implemented. So let's say you have one master and one slave, and you don't have any synchronization. So actually, when slave is doing frame 0 on half of the screen, the master would have flipped to still on the frame -1, and that's where you see the tearing. Now, let's say you enable the port sync for the next frame, and then what it does in the hardware is that you enable the port sync mode on the slave, and you tell the hardware, okay, this is the other master this is the other port that is configured as a master. And what slave does is it just freezes the slave timings. The hardware just freezes the slave timings, and it waits in its B blank to get the synchronization signal, to get a trigger from the master. So when the master is ready, it's going to send this trigger to the slave, and then thereon, the master and the slave, all the counters, it's line and frame synchronized thereon for both the master and the slave. So let's see how it looks like on the atomic KMS pipeline, right? So you have the 8K frame. The changes that we had to do were, first is the atomic check, and that's where you send the two separate tiles on two separate CRTCs. And this is where we had to implement a policy in the driver where we decide which tile becomes the master and which tile becomes the slave. So the last tile becomes the master, so the connector that is associated with the last tile is the master connector, and that's where you save the master CRTC state with all the slave information. So you have to actually go back and loop through all the connectors, find the slaves, and then you save the slave in terms of the bit mask. You do the same thing for the slave because you need to have the association between the master and the slave. The slave needs to know what port is the master in this tiled mode set. So we have these new variables in the slave CRTC state where we save the pointer to the master transcoder. And all this information gets used in the atomic commit phase. And this is where you actually configure the hardware and write to the hardware registers and say that, okay, you have to enable the port sync mode, and this is the master select. So the slave transcoder uses the slave CRTC state and the pointers to the master transcoder to actually tell the hardware that, okay, this is the master, this port is going to act as a master, and enable the port sync mode. Then we configure the master. So now both the ports are ready, and at this point, the hardware is configured and it knows it has lockstep the slave and the master timings. And then in that case, we should not see any tearing. So I'm just going to go over the sequence of things that happen in the atomic kernel mode setting. First thing, you connect the monitor, you get the hot plug signal. User space is going to probe the connector and get the connector information. That's when the EDID sends out the display ID block, which will have all the tile information. And the kernel sets the connector tile property, exposes that to the user space. User space reads the tile property and creates the frame buffer based on the tile information, sets up the two CRTCs or more if there are multiple tiles. and then it sets up the CRTC offsets based on the tile offsets. And then all it has to do is call the atomic mode set, and then rest, everything happens in the kernel. So in the kernel, like I explained, first is the atomic check, where we had to make a lot of changes to ensure that the master and the slave CRTC states are set up correctly, where the slave has a pointer to the correct master, slave mask will be 0 for the slave, and then for the master, the pointer is null for the master, but it saves off the bit mask for the slave. The reason we use the bit mask is because even though for this monitor there's only one slave, this solution could be used for cases like digital signage boards where you have one master and like 5 or 10 different slaves. So you need to have a bit mask where it saves all the associated slave ports with the master. Now, the biggest change was in the atomic commit. So in this case, in the tiled panel case, what happens is all the updates only happen in the atomic commit for the master. So you're in the atomic commit for the master. In that one, first step you have to do is get all the, trace back all the pointers and get the slave CRTC state. You obtain the slave CRTC state, you obtain what slaves are associated with that master, and then enable the slave transcoders and ports first, because remember, we have to enable the port sync mode in the slave. So you have to do all the enabling for the slaves first. And you get the slave ready, you link train the slave, but you don't want to start spitting out the actual data bits here on the slave yet, because the master is not configured. So you leave the DPTP control to idle. What that means is it's just outputting the idle patterns at that time. It's not outputting the actual data. Then you configure the master ports, PLLs, enable the master transcoder, leave that again to output the idle patterns on the actual cable. Then you go back and go back to your slave CRTC and set the DPTP control to normal. So now it's outputting the actual data, but the timings are such that it's waiting for that sync signal to come from the master. So it's just waiting in its V blank and waiting for the master to be ready and send that synchronization signal. Then you configure the master to normal, and then the master at this point is ready. It sends the V blank and the trigger signal, and the slave timings, all the line and the frame counters are back in the game again. And then you do the plane updates, the pipe register updates, the page flips for both master and slave together, and here you go, you don't have any tearing. So how did we validate this? So far, I have only validated this with IGT. There's still some issues that I have with actually validating with X server, Wayland. So, but the kernel functionality works because I was able to test the page flip timestamps using an IGT test. So wrote this IGT test. It's already upstreamed in the IGT suite. KMS DP tile display.c, and we also wrote the tile property parser to decode the tile information. So that's going to read the tile property and get the tile information from the kernel and spit out the data to user space in terms of the tile offsets, tile location, everything that it needs to set up that frame buffer and CRTC offsets. That's also upstream to the IGT KMS in the IGT lib. So we validate this by actually capturing those page flip events. We talked about those again a lot of times in earlier this morning. So we capture the page flip events that we get on both the CRTCs and make sure that they happen close enough. So we have to make sure that it happens in the same V blank. So we make sure it's within 10 microseconds. And I think huge kudos to our interns, Madhumita, who helped write these tests, and then Simon sir for reviewing and a lot of invaluable feedback. So now we have everything working upstream. So on the left side, you see is what we had without the transcoder port sync, and it shows the page flip timestamps for 2 CRTCs, and it's like 500 microseconds apart. So, and that's where you would see tearing, and I have pictures of that in the next slide. And then what I see now when I run the test is it's barely like 1 microsecond apart. So the page flip events occur on both the CRTCs at the same time, and no tears, no tears either. So all the patches, the kernel patches for implementing the transcoder port sync feature are on the mailing list and expected to land in 5.4 kernel. I'm waiting to fix just one last CI failure, and then they will be good to go because it's all reviewed. Um, so results, because I couldn't carry my 8K monitor here, I just have pictures, but these are the pictures taken on the 8K, the Dell 8K monitor that I have in my cube. This is what I was seeing when I started this project, and it was I would see a lot of tearing even with a simple RGB pattern. Um, and then that's the true 8K image, which I got from internet, and then, but it was able to display that because the planes, everything can handle it, but then the tearing was really, really bad. And then what I have now is, ta-da, no tears. um, yep. So that's all I had.
Question is that what kind of, what should I say, collaboration did you have with pre-silicon, I mean, the RTL designer, pre-silicon verification people, post-silicon verification people? I'm sure you know
Right.
who these people are. I'm just
Yeah,
curious,
yeah,
what kind of interaction did you have with them?
yeah.
Did they like test some of this functionality
Yeah.
on their end before you like ported to Linux?
Sure. So yeah, so on our hardware team, we do have, post-silicon, pre-silicon hardware validation as well, and that happens way before, we even get the pre-production hardware. So they absolutely, they have validated this feature on their end, and they have their entirely different test suite which they use for validating all the timestamps, all the features on their end. So yeah, it is validated.
Okay, so the follow-up question, now that you mentioned that, is, do you have some kind of ways, this sounds, at least from my recollection, similar to the AMD display core thing, where they were trying to kind of more combine, the post-silicon people and the software bring-up people to use the same kind of code. What kind of situation do you have regarding that?
I don't think we have gone that far to, looking at if we can code share some of the test code with the hardware validation folks. But I mean, I think we can get there because there are a lot of these features where the test code might actually look similar in terms of the math or, yeah, so, but currently we don't have any code sharing with the hardware validation.
All right, thank you.
Do you have any concept of like a plane bridging over the two tile displays? Like, I guess you would have to virtualize the plane and then take up two hardware overlays to scan it out, or is that just crazy?
Uh, so right now it would just be two separate planes on two separate CRTCs. So we don't do anything special for allocating the planes to. So are you saying plane mapping to the hardware planes?
So I guess the tile displays are presented to user space as two separate displays, right?
Right.
Okay.
Yeah.
So then it would handle planes
Yeah.
just
So
the same as it would if you had two displays.
exactly. So we run into that scenario actually on a case where we would have a panel that takes up only one output port, and then we still have to use two CRTCs because of the pipe limitation that I spoke earlier. So in that case, it acts as one CRTC to the user space. Internally, we use two CRTCs, and in that case, we do have to do splitting of the planes and plane state, everything. So those patches are also on the mailing list.
Okay.
Yeah, so
Yeah, that was what I
your
was
review
wondering
would
about.
be helpful.
Thanks.
No question really here. Just saying this is, looks like a good and interesting implementation. We've done similar stuff in AMD hardware, and I kind of like your solution in particular for that 8K, like you mentioned, even if you present one CRTC to user mode for probably the DSC case.
Yeah, for DSC case.
And we were talking last year about how to potentially solve this. It's a great solution for it, I think.
Yes, yeah, thank you. And with the DSC case, I think it gets a lot more complicated. So again, your reviews, and maybe we can discuss that a little bit more later, because those patches are still far from landing.
Sure.
Hi. The question is regarding how you actually model it. So you said that it's two CRTCs. Like, have you considered actually using a single CRTC and two connectors and creating a virtually, a virtual CRTC, I mean? A virtual connector which kind of captures both?
So I think, so in this case, because the monitor itself
Yeah.
just advertises itself as a tiled monitor,
Yeah.
it, logically ends up using two CRTCs. That's one thing.
Okay.
The other is we have to use two CRTCs for 8K because of the limitation.
Of the pipe, but two pipes can be mapped to
Single connector.
single CRTC?
So pipe and CRTC is the same. So two
That's how
pipes
it's mapped?
equals two CRTCs in the hardware.
So why I'm saying is that from the user space, if it is like virtualized into a single image, right, then the composition is just as a single image,
Single
right?
frame buffer,
Otherwise,
yeah.
you are now actually driving them as two different displays. That's what I'm saying.
Yes. So I don't really know if this was special for tiled cases, but this code has been there in the user space for a really long time, where if it sees a tiled display, then it has to, it actually treats it as two separate displays. With the tile information, it will do two modesets, it will use two CRTCs. And I
Like,
think some of
what
the...
I'm saying is that if it is expanded eventually to a display that doesn't need tile, but it can still support an 8K with a single,
Sure.
right?
Yes.
Then you still have to manage that, right? So
Right. So that's the second configuration that I spoke about earlier. So that's where it will be just one display. It won't be a tile display. Internally, we would still use two CRTCs, but then to the user space, it would still be just one CRTC, one frame buffer. And we split it across two CRTCs, and then we join it back
So
to
you
send it
create a
across
virtual-
one port.
Internally, you manage it as a virtual CRTC. Is that what it is? Or it is still exposed? You're saying it's...
User space will be seeing it as one virtual, one
Yeah, okay.
CRTC,
Yeah,
but
that's what I'm-
internally it will be on two pipes or
Okay.
two CRTCs.
Okay.
What's different is it will come out through just one port. We have a hardware that will join the outputs from two CRTCs and just output it through one DisplayPort.
Okay. Okay.
The original MST support for the original tiled Dell displays, that required two CRTCs, but could drive over one DisplayPort cable. But it did it in MST mode. So there
Yeah.
are 8K displays that are not MST now?
Yeah, this
Oh.
the 8K displays are two SST DP ports.
Okay, so it looks just like one DisplayPort then.
It actually has two DisplayPorts. DisplayPort connectors on the monitor end.
No, on the current, but you were talking about an upcoming monitor that has a single DisplayPort connection and does 8K over one wire?
Yes, yeah.
Oh,
But
okay.
we,
And not MST
I haven't
anymore.
I haven't seen that monitor yet. We have a emulated board that we use for testing, but as far as I know, there is none out in the market.
Okay.
But that would need display stream compression because we still cannot handle 8K on a single connector.
And you are going to show that as one virtual CRTC?
Yes.
Okay, because when we did the original MST support for the original Dell 4K DP monitor that was tiled, we looked at using virtual CRTCs, and the problem we had was that then user space would get very confused because user space would get, suddenly one of its CRTCs would disappear.
Yes, yeah.
And so we decided to just punt and expose it all to user space, and that worked out fine because the applications can't see it. It's hidden from the application. So unless you need to do that, we already have the tiled support, and there's no particular reason to not do the tiling and not show it up to user space.
But what if the monitor is not tiled? I mean, that monitor is not a tiled monitor. It is one single monitor. It's not going to
But
have
it-
a
but-
tile
but-
property.
But you're using oh, it's not going to have a tiling property.
Yes, yeah, it's a
Ah.
single
You could-
non-tiled
Yeah, one can
monitor.
imagine synthesizing the tiling properties, but yeah.
Right,
It
yeah.
sounds like you're coming up with a good solution.
We did
I'm
think
just
of that,
I'm just
yeah.
concerned about hiding the disappearing CRTC from user space and how user space is going to respond. Are you going to like steal one of the CRTCs all the time?
Yes. So there are some patches on the mailing list where we have separated the UAPI state and the hardware state. So the hardware state is what would be the, what would use two CRTCs on the Intel hardware, and then UAPI state that we expose to the user space, which would still act as one display, one CRTC, one set of planes.
So you're going to the question I have is, so is that going to appear to user space as a variable number of CRTCs?
It will hide the second CRTC.
So you'll
from-
never see the second CRTC.
No.
So what if I plug in two smaller monitors? Do I get fewer CRTCs?
Two smaller monitors
So-
won't
so
use
if I-
multiple CRTCs.
So if I have an 8K display, I'll have so say the hardware has 3 CRTCs, and you might want to use 2 for 8K, right? So is the user space going to ever see 3 CRTCs, or is it always going to see 2 CRTCs?
Just make it easy and limit what you expose to non-atomic user space. And atomic user space does test only and gets to.
But your
sometimes see more.
CRTC disappears.
Yeah.
It doesn't disappear. It just might not be usable all the time.
Oh.
Yeah, so
Oh, thank you.
So
Yeah,
from-
that will work.
from our side, we have other use cases where we also do that, where
Yep.
a CRTC becomes unusable, or actually in this case it's still usable, but we might
Hide it. Right?
we might send one output through 2 CRTCs for power saving mode, because it allows us to drive certain hardware blocks at a lower clock.
Yep.
And then when we need it, we're going to start reusing it. And in the 8K case, I think the problem is the clocks are just not fast enough on
Yeah,
any
obviously.
hardware, Intel or AMD, to
Yep.
do this. So we'll need to steal a CRTC, and you can't use it while you're doing 8K.
Yeah. Yeah. If the 8K monitor is hot plugged, then if it's 3 CRTCs on the hardware, then it can only do 8K plus one other.
So for non-atomic mode setting, if you don't set the atomic bit, you'll show n-1 CRTC, so you could hot plug an 8K display. That seems like a good solution.
Yeah. Yeah, and again, I think those patches still need a lot of review, so if you have more feedback.
My only concern is what's going to happen. What is user space going to see? Is it a variable number of CRTCs, or is it that you can only get this configuration by using atomic? And that second answer seems like a good answer.
Yes,
The first
yeah.
answer seems like
Only
a bad
for
answer.
atomic. Yep.
Okay, perfect. Thank you. Now I know what my question was.
Thank you. Any more questions? Okay. Thank you.